Today we'll be discussing biogas yield and volume. Typically, biogas composition is about 55 to 70% methane and about 30 to 45% carbon dioxide. The proportion of methane to carbon dioxide, as well as the volume of biogas produced and the quality of the biogas, will depend on the composition of the substrate used, the operating conditions of the digester, and the retention time. In this video, we'll be applying the Buswell formula. So this is the Buswell formula. This was developed in 1952. We'll be applying the Buswell formula to determine biogas yield from glucose, acetic acid, pyruvate, and lipid. So the Buswell equation will help us get the right stoichiometry, easily get the right stoichiometry. And when we get the right stoichiometry, we can use that to determine the yield and the proportion of methane to carbon dioxide composition of the biogas. The Buswell equation is a general simplified reaction. And this particular equation we're using here assumes 100% conversion of the substrate to biogas. There's another variant of the Buswell equation which would look at later on in this video. So go ahead and look at the first substrate. That's glucose, and I've reproduced the Buswell equation here. So we look at this equation, we would find out that the A is 6, the B is 12, the C is 6. So if you now insert this equation into these numbers accordingly into these various coefficients, we'll find out that we'll have 6 minus 6 for the A minus B, which is 12 over 4 minus C, which is 6 over 2. And we'll do that for all the compounds. We'll find out that water has 0 coefficient or 0 moles. That's implying there's no water, which means water is not necessary for this reaction to proceed. And then we'll find out the number of moles of CO2 is 3 and the number of moles of methane is 3. So 1 mole of glucose will give us 3 moles of carbon dioxide and 3 moles of methane. Now the volumetric fraction of carbon dioxide will therefore be 3, which is the 3 moles of carbon dioxide, over 3 plus 3, the 3 moles of carbon dioxide and the 3 moles of methane. And that will give you 50%. If we do the same thing for methane, we'll find out that it's 50. So why are we using the number of moles for the volumetric fraction? This is simply based on Avogadro's principle, which states that all gases, the volume occupied by 1 mole of all gases at standard condition is 22.4 liters. So 24 liters per mole of gas. So regardless of the gas, the volume will be the same under standard conditions. So we can just use the number of moles and to find out the fraction of the various components of biogas. So how about the yield and volume per kilogram of substrate? The volumetric yield per kilogram of substrate. If we look at the mass of glucose, the mass of 1 mole of glucose is 180 grams, and this 1 mole of glucose will produce 3 moles of methane and 3 moles of CO2. And so 3 moles methane, 3 moles will give us a total of 6. Since each mole contains the same volume, we can just lump it up, and it means 180 grams of glucose will produce 6 times 22.4. This is from the Avogadro's principle, which says each mole will occupy 22 would be 22.4 liters. volume. So that would give us 134.4 liters or 0.1344 cubic meter of biogas. So proportionally, if 180 grams will give us 0.1344 cubic meter, then 1000 gram, which is 1 kg of the substrate glucose, will produce 0.1344 times the 1000 over 180, which will give us 0.747 cubic meter of biogas. Now, in finding the volume, if we didn't use the Avogadro's number, we can find it using the formula V equals to nRT over P, and we have the definition of all these terms, V volume. You can pause this video and look at the definition of the terms and go through the calculation if you wish, but this is just the same. It will give you the same. This from where we get the Avogadro's number, so this will give you the same volume. So go to the next substrate, which is acetic acid. Just like we did in glucose, if we have the Buswell equation, our A, B, C, we set in the appropriate values to find the coefficient of all the other compounds. So find out that 1 mole of acetic acid produces 1 mole of carbon dioxide and 1 mole of methane. Again, you can pause it to, if you want to be more detailed in going through what I did, you can pause the video. And then, just like we did for glucose, we can find the volume of biogas. We know 1 mole of acetic acid is about 60 grams. And this 60 grams will produce 2 moles of a mole each of methane and carbon dioxide, which will be 2 moles, and each mole will be 22.4 liter, and we end up getting 0.0448 cubic meter of biogas. And then when we divide it, use our proportionality, we're going to have 0.747 cubic meter of biogas, which is the same as what we got previously from glucose. So the volumetric yield per kilogram of substrate is the same for these two substrates. We look at pyruvate, which is an important compound in most biological processes. It's a common intermediate for most metabolic reactions. That's just why I included it. So applying the Buswell equation, again, we have our A, B, C. This will be A, B, C, A, B, C. You apply the equation, we'll find out that 1 mole of pyruvate, would produce 1.875 mole of carbon dioxide and 1.125 moles of methane. In this case, we'll find out that water is necessary for this reaction, and then we find out that more carbon dioxide is produced than methane. So on a molar basis, 1 mole of pyruvate will produce more gas, biogas volume, more volume of biogas, because it's 1.875 plus this will be 3 moles, so that's 3 times 22.4, which is more than 2 times 22.4, which is the case of acetic acid. So 1 mole of pyruvate will produce more biogas, but the quality of this biogas is lesser because we have a higher proportion of that biogas is CO2, whereas acetic acid has 50% methane, 50% carbon dioxide. This has relatively less methane. So carbon dioxide is non-combustible, so it's just going to absorb some of the heat because it's going to be heated up if combusted, and that would reduce the overall heat. Just like we did for the substance, we can find the volume of biogas produced from 1 kilogram of pyruvate, and we see that 1 kilogram of pyruvate will produce 0.772 cubic meter of biogas, which is not too different from what we've calculated previously. Now we can look at lipids. I'm just using a general formula here for lipids. When we apply the Buswell equation, we'll find out that 1 mole of lipid will produce 2.25 mole of carbon dioxide and 5.75 mole of methane. This is so different from what we've looked at previously. We'll find out that methane is about 2.5 times the amount of methane in the biogas is about 2.5 times the amount of carbon dioxide. And so we see that the fraction of methane is about 72%, while carbon dioxide is just 28%. And we also see, just like with pyruvate, that water is required here too. For glucose and acetic acid, water was not necessary, but for pyruvate and lipid, water is necessary for this reaction. So one of the reasons why what do we call it? Why this lipids produces more methane than carbon dioxide, this high level of methane, it's because it's less oxygenated. It has less oxygen. If we look at the other feedstocks, let's see, pyruvate, you see we have the oxygen, the mass of oxygen is more than the mass of carbon. Acetic, the mass of oxygen is more than the mass of carbon. Glucose the same, we have the mass of oxygen. So we have high quantity of oxygen in all the other substrates, but in lipid, oxygen is very little. It's just a tiny fraction of the mass. And because it's less oxygenated, we see from this equation here that the oxygen goes into CO2 production, and that's true for all the other feedstock, because this we're having only methane and carbon dioxide, so any oxygen goes into CO2 production. So the more oxygen we have, the more CO2 will be produced. The less oxygen we have, the less CO2 will be produced. So that's the reason, and we can go on to calculate the volume. Again, when we follow the same procedure we did for those other three substances, we'll find out that 1 kilogram of lipid will produce 1.4 cubic meter of biogas, which is almost double what we had for the other feedstocks. So not only do lipids give us very high methane composition in the biogas, which in other words gives us better quality biogas, they give us more volume of biogas. So this looks like a very interesting and desirable substrate for anaerobic digestion. So here I have a table comparing them briefly. We have a mole of, so these are the substrate. 1 mole of the substrate will produce, these are the moles of CO2 produced, the mole of methane produced, and we have the what do I call it, the volumetric fraction of methane in the biogas. So glucose and acetic acid will give us 50% methane in the biogas, and pyruvate will give us 38%, and lipids will give us 72%. Of course, different lipids may vary slightly, but most of them will be around this number, 70 and above. And we see that for this three substrate, the volumetric yield per kilogram of substrate is the same. It's not the same, sorry. It's similar, it's not too different, but lipid gives us quite a high biogas yield. So normally for most reactions, for example ethanol fermentation, if we find the stoichiometry of how much ethanol will be produced from sugars, we know that in actual case we might not get that amount. It will be lesser, or maybe close, it could be close, but usually lesser than what is stoichiometrically determined. For most reactions, the stoichiometry is like the ideal case, but in biomass, usually the percentage of methane calculated is usually higher in actual case than is stoichiometrically calculated. And one of the reasons for this is because in practical systems, some of the CO2 gets dissolved in the processed water. This will look like something trivial or not significant, but we'll look at an example to see how this can be significant. And I touched on this in the earlier video for Module 2. I touched on this reason how methane could have higher yield than stoichiometrically determined. But we'll look at one of the examples we just looked at and see. Take a quick look at one of these examples. So we'll look at pyruvate again. It's estimated that 1.8 gram of CO2 dissolves in 1 liter of processed water at normal conditions, and this normal condition is defined as 1 atmosphere, normal atmospheric pressure, and ambient temperature, which would be like room temperature of 25 degrees C. So I decided to reformulate the equation so that we have water equivalents of 1 liter water, and that would be 0.55 moles of water will give us 1 liter, and that would mean that we'll have less than 1 mole of methane. So if we look at this reaction, we'll be producing 0.137 carbon dioxide, and this would give us a mass of 6.1 grams. So the mass would just be the molar mass times the number of moles, and that will give us 6.1 gram. And since we have 1 liter of water, we assume that, I'm assuming here that 1.8 gram is totally dissolved in the processed water. Now this depends on a lot of things. The retention time, if you have a longer retention time, if you have you could have all of this dissolved. If it's shorter, you could have way less than this dissolved. Of course, we're just assuming a particular temperature now, which is ambient temperature, but the solubility will depend, of course, on the temperature, pressure, and other factors. But we're assuming that things are normal and all of 1.8 gram dissolves. That will leave us with 4.3 grams of CO2 that was produced. This 4.3 grams is equivalent to 0.097 moles of CO2. So left in the headspace that will be collected, we have originally 0.137 produced, 0.04 dissolves in water, so we have 0.097 in the headspace. Now the solubility of carbon dioxide relative to methane is about 400 to 1. So carbon dioxide is way soluble in water at ambient condition than methane. So if 0.04 moles of carbon dioxide dissolves, then we'll be anticipating that 400 times less of methane will be dissolved, which will be 0.001 moles of methane, which is negligible. We can subtract it, and that would give us 9. So that would be 0.0829, which is still approximately 0.083. So we'll just leave it like that, and when we do our new calculation, we have 0.083 moles of methane. Like we said, there's only 0.097 that is left in the headspace, plus 0.083, and we'll find out that we're getting about 46% of methane compared to what we had calculated earlier on, which is about 37.5 or 38%. So you can see that by reason of CO2 just dissolving in the water, the proportion of methane you collect in your headspace in your biogas is higher than what you calculate stoichiometrically. Yeah, I said I was going to touch on another variant of Buswell equation. So this is it, very similar to what we just have, but this will be for substrates containing nitrogen and sulfur or sulfur. So proteins, if you have proteins, you can use this equation. You can also use this for carbohydrates. The n would end up being zeros, the s would end up being zeros. So you can use this formula, this a more general formula from most feedstock. Yeah, so it's the same principle. You just insert your value and you have your, but here we see that biogas is not just the sole product. We have some ammonia and with the hydrogen sulfide produced too. That brings me, let's look back at this table. If we had done this for proteins, we might be getting biogas yield of about 60 something, so lipid will still be higher. So we'll have methane yield will be better than glucose and acetic acid when you use proteins, but it will still be less than lipids. So overall lipids will still give us the better yield. So I will stop here and we'll meet some other time. Have a great day. Bye.